Good morning, everyone. Welcome to today's webinar brought to you by Thermtest. My name is Angela and I'll be the moderator today. We're here to delve into the exciting world of thermal conductivity testing, specifically focusing on Thermtest's innovative iTransient algorithm and its applications in Transient Plane Source methods. Our speaker today is the accomplished physics lead at Thermtest, Mr. David Landry. With 5 years of experience, he's made significant contributions in upgrading the company's measurement platforms and testing techniques. Today's presentation will guide us through an introduction to iTransient, an overview of the iTPS algorithm, its power selection details, and mapping the scouting transient to test parameters. We will also discover how automated testing parameters combined with transient methods like iTHW, and iTLS can optimize testing efficiency and accuracy. Towards the end of our webinar, we will have a question and answer session. Although this will occur at the conclusion of the presentation, we invite you to type your questions into the chat and David will answer them at the end of the webinar. So without further delay, let's dive into this enriching experience. So over to you, David.
Hi, I'm David Landry. Can everyone see my screen that I'm sharing?
Yep, we can see your screen.
Okay. Thank you, Angela, for that introduction. And yeah, I'll be covering the iTransient algorithm, which is for the intelligent measurement of thermal conductivity. There we go. So the iTransient is designed to automate the selection of testing parameters such that the theory of operations for any transient method is still followed. That is, the assumptions that let the method work, that are usually defined within the sort of seminal papers that create them, those are still followed. The iTransient applies to 3 methods currently: the iTHW, or the Transient Hot Wire, the Transient Line Source, and the Transient Plane Source. iTHW and iTLS are fairly simple algorithms because the methods themselves are much more restricted and narrow in scope. However, the Transient Plane Source is a very wide-ranging instrument, and so the iTransient algorithm for it is very complicated. And it'll be the one that I'll be talking about today.
David, are you aware that you are muted right now?
No, I was not. How long have I been muted for?
You said the last thing you said was when you switched to the slide.
Oh,
I thought for a
sorry
second it
about
was
that.
a glitch, but
No, I accidentally hit a key on my keyboard instead of space, and I think that might have been M for mute. Okay, sorry about that. Back into it then. The thing that makes the transient plane source difficult to select its optimal parameters for is that it's 3 parameters that you need to select for instead of 1 or 2, as with the THW or TLS. And all 3 of these parameters feed back into each other. And on top of that, the parameters also depend on the sample dimensions and the material properties. So there are 3 things that the iTransient will select for in the in its algorithm, the sensor size, first off, the test duration, and the test power. Normally, the sensor size and the test duration are very related to each other. And if one of them is selected incorrectly, it can make it seem like the other was also selected incorrectly. And so actually making that correct selection can become very difficult. Currently, users have to rely on experience and iteration to get the best test parameters. And that means changing the sensor after having done an experiment, or changing the test duration and seeing how well the test fits, or doing a whole slew of experiments and selecting some subsection of them. That's very inefficient in terms of time. And so the iTransient algorithm is designed to resolve that, such that it intelligently chooses test parameters with minimal user input. Give a brief overview of the algorithm now before going into the details of each step. So that minimal user input I just mentioned is actually just the sample dimensions. That's all the user has to enter. And then they press the sensor selection button, and it gives a sensor recommendation. From here, the user or lab technician or whoever's running the experiment can follow the sensor recommendation, or they can choose a different sensor. Once that's done and everything is set up, they press the iTPS button, and everything after that is automatic. The user could walk away and come back in 5 to 10 minutes and have things be finished. So the automatic portion begins with the category transient, which I'll get into soon, which selects a sort of base category that the material falls into. And then we come to the meat of the algorithm, which is the parameter scouting transient and the calculation that gets performed on that scouting transient. The scouting transient is a fairly lengthy test, up to 160 seconds, and calculations get performed while the test is ongoing, and they determine if the test continues or if the test terminates. Once the termination condition has been reached, that means that there's a good enough estimate for the thermal properties that the algorithm feels confident in. Once this is reached, then from those we can recommend an optimal test duration as well as a power. So we see that the sensor was recommended fairly early on. At the end, the test duration and power got recommended. That's all three of the sort of unknowns in this system. Let's go over how the sensor gets recommended based off of the sample dimensions. So the sample dimensions are critical for determining which kind of TPS test will happen. There's bulk or slab, and these are separated by which boundaries are assumed to be infinite. A bulk measurement assumes that the boundaries are infinite, and a slab measurement assumes that only the radial boundary is infinite and that the axial boundary is actually finite. So the samples can be characterized with an available probing depth, which is how much distance or volume is available to be tested. And it's basically the minimum distance from the sensor to the boundary, or to the radial boundary for slab. In addition to the available probing depth, there's an applied probing depth, which is how far the heat has significantly penetrated from a test. And this will depend on the test duration. As you can imagine, as you let the sensor heat things, the heat will travel further. And the goal of the sensor selection is to maximize the applied probing depth while not surpassing the available probing depth, as well as maximizing the test quality based off of some established rules. The established rules are to help determine the sensitivity of the measurement to different parameters. Once a sensor is selected and the user hits the iTPS button, we get to the category scouting, or the power selection, the initial power selection. And the category scouting, its goal is to sort the material, or sort the sample into one of 5 categories, from very low conductivity to very high conductivity. And each category has a set of typical test parameters, duration and power, that will perform adequately. And those will be used later once the category has been actually determined. The category scouting transient is a very short measurement using a safe power that can be applied to any material tested. So you can imagine that a safe power for copper might not be the same as a safe power for an insulator, but this is selected such that basically an insulator won't heat up too much while still providing enough power to recognize things from noise. In this transient, several factors get considered from the data: the actual temperature rise at certain points, as well as the temperature slope with respect to time, or some function of time at specific intervals. And so once the data has been considered, a category gets determined, and then the initial power gets selected based on the category's typical parameters. This is an initial power because in some cases, such as high thermal contact resistance, this power selection can be off by one category, usually by one category at the most, usually. This is the case during the next step. The power will get adjusted to a new power. An example of this is if the power, or if the category was selected to be too conductive, then the temperature might rise too high, and the sensor temperature will exceed 10 degrees above ambient. And so the selected power is passed to the next step of the iTPS, which is the scouting transient. And so the scouting transient takes the form of, first, a 4-second collection of data, which we have an example of on screen. And for this initially collected data, we calculate different windows in the same way that a user might calculate things in the analysis application, but all done automatically. So there are quite a few predefined windows where we calculate the thermal properties and the quality of fit. So we start with a very small window of, say, 0.15 seconds to 1 second. And the algorithm iterates things until it reaches the final window for the batch, which is 0.15 seconds to 20 seconds, or to 4 seconds demonstrated here. The windows will change in starting and ending points, and the computer will store the best fit thermal properties as well as the quality fit. And if this quality starts to deteriorate, then that's what determines if the testing should stop. If the fitting quality deteriorates, then that means all further testing will just be worse than some previous window that was the best of them. If that isn't the case, however, and the fitting quality shows improvement, then the transient continues past these 4 seconds, and we get a more typical scouting transient, where we have pauses in the data collection to transfer over the data for calculation. And we have a new batch of data shown and a little bit of another batch in this example. So with the new data, it can start calculating new windows that are available. Prior to this, 4 seconds was the maximum time. So now it can calculate 0.15 seconds to 8 seconds, and other such windows all the way up to 14 seconds here, just based off of what's in the specifics of the algorithm. All the previous information is still stored and remembered, including the thermal properties and the quality of fit. So all the new thermal properties and quality of fits get added to that. If the fitting condition gets reached now, or the windows over the new batch of data started to deteriorate, then the termination condition gets reached, and that's passed to the controller, and the measurement will end prematurely before reaching 160 seconds or 80 seconds, depending on the sensor. We can see that this happened, and calculations went from 16 seconds to 20 seconds while the measurement was still ongoing before the fitting condition or the termination condition had been reached. So once this happens, we take a special average of all the different windows that were tested, and we get the special average of thermal conductivity and thermal diffusivity, and we map those to a test power and a test duration. The duration will be based on the sample dimensions as well as the thermal properties, and the power will be based on duration and the thermal properties such that the temperature rise is both not too large and not too small, to distinguish things from noise and to make sure the sample doesn't heat up too much. So, in conclusion, we have our initial problem, which was selecting optimal test parameters for the transient plane source, which requires either experience and/or iteration on the experiment, which can be lengthy and unintuitive for a new user especially. And the solution we've come to is the iTransient algorithm, which will automate the process of sensor selection and duration and power recommendation. The sensor gets recommended based off of sample dimensions, and then the test duration and power are recommended by an intelligent scouting and calculation algorithm. Thank you, everyone, for listening to me. If you have any questions, please type them into the chat and I'll answer them. I'll just wait a minute here for anyone to type anything in. So it doesn't seem like there are any questions. Thank you, everyone, for joining me, and have a nice day.
Thanks so much for joining our webinar on iTransient for automation of thermal conductivity methods with Mr. David Landry. Thank you, David, for taking time out of your busy schedule to provide this educational opportunity for us. And keep an eye out on your inbox. We will be setting out the webinar recording within the next few days. And if you have any further questions, please don't hesitate to send an email to marketing@thermtest.com, and a member of our team will gladly assist. I hope everyone has a wonderful day, and that concludes our webinar today. Bye.